Of chapter 7. Okay, so last session we discussed electrophilic dibromination of alkenes. In this section, we're going to talk about variants to this mechanism and modifications that can be made to these electrophilic addition mechanisms and reactions in order to increase the amount of available functionality we can incorporate into our alkene. So, as we alluded to in our discussion of dibromination, the bromonium and halonium intermediate can be intercepted with other nucleophiles, such as water, alcohols, or internal nucleophiles. So the most common example of this is the generation of what is known as a halohydrin via addition of a nucleophile, such as water or an alcohol. So the actual functional reagent that really initiates this reaction is our dihalogen in water. So although the dihalogen can be used, it's far more common to use a halogen equivalent such as N-bromosuccinimide. N-bromosuccinimide can be thought of as a source of Br+, so you minimize the amount of competing dibromination. So N-bromosuccinimide can either be thought of as a direct source of Br+, or a source of a very, very, very small concentration of bromine in solution at any given time. So one thing that I want you to note, an internal nucleophile would be like a nucleophile that's present in your molecule. And we'll look at an example of this, such as, for example, if you have an alcohol already attached to your molecule, it can function as an internal nucleophile for intramolecular reaction. We'll see an example of that later on. Okay, so one thing to keep in mind, if we consider our electronegativity values, nitrogen is slightly more electronegative than bromine. So this bromine has a functional partial positive charge and can function as an electrophilic source of bromine. Okay, so if you see NBS or N-bromosuccinimide, it's just functioning as an equivalent of Br+, and that minimizes this dibromination side product. Okay, so let's talk a little bit about the mechanism for this. Let's talk a little bit about the mechanism for this. So we have our Br+ equivalent, and it can add to either face of the alkene in most cases. So that in turn means, as a result, we typically see a mixture of enantiomers. So for example, if we have our alkene, we can observe addition from either the top or bottom face. In each case, you end up with a set of molecules that are non-superimposable mirror images or enantiomers. So Br+ can add to either face. Okay, once that's set up and you have your bromonium intermediate, rather than intercepting our bromonium intermediate with an equivalent of bromide, we instead intercept our bromonium intermediate with our alcohol or water. This attack occurs from the opposite face of the bromonium ion, and as a result, you end up with a trans product or an anti-addition product. That's important. So the stereochemical outcome is the same as in dibromination. Now, one important thing to note is that water attacks the most substituted carbon, or the carbon that has the most cationic character. We're not actually making a carbocation. Instead, we just observe regioselectivity for the most substituted carbon, or more exactly, the carbon that can most accommodate a positive charge. So we're working under Markovnikov selectivity in regiochemistry. The final step is the resulting alcohol is deprotonated by the solvent or succinimide to get your final halohydrin. Okay. So notice we generate the trans product. That's because, noting in our mechanism, the attack occurs on the opposite face to our halonium. That's why we observe our trans product. Does this idea make sense to everyone? It's very similar mechanistically to dibromination, except rather than attacking with bromide, we're attacking with water or another alcohol. It's really important to note the stereochemistry because we're going to look at different reactions with slightly different stereochemical outcomes. Okay, so one thing to note is that halohydrin formation follows Markovnikov selectivity, favoring addition of the alcohol or water at the most substituted carbon that can most readily stabilize a positive charge. So in this case, we have the choice between a primary position and a secondary benzylic position. Which of these positions is more substituted and which of these positions can more readily stabilize a positive charge? The secondary, exactly right. And that's why we observe preferential attack of our alcohol at the secondary position. So we can see very clearly from our observed product distributions that we're working under Markovnikov patterns of regioselectivity. Does that idea make sense? Okay, so why is this happening? Well, although a formal cation is not generated, the carbon-bromine bond attached to the more substituted carbon is weaker and more reactive towards displacement. So for example, in our first step, we treat with N-bromosuccinimide. We generate our bromonium intermediate. And now if we have a choice, we can either attack at the secondary or the tertiary position. And if we think a little bit about which position can more readily stabilize this positive charge, in general, are cations more stable at a tertiary or secondary position? Which position can more effectively stabilize our positive charge? Which position, tertiary or secondary? Tertiary, yep. That's why we observe preferential attack at the tertiary position, because it's the most electrophilic site, can most readily accommodate a partial positive charge, and in turn is more reactive towards attack by our nucleophile. We are not making a formal carbocation. We do not see the typical carbocation shifts that we would observe for mechanisms that go through a carbocation, and we observed a defined stereochemical outcome. So even we get a set of a product plus its enantiomer. We do not observe the other regioisomer in significant amounts. Okay. And the way that you can think of this, as it's indicated in the drawing, the carbon-bromine bond attached to the more substituted carbon is weaker, and as a result, that tertiary carbon has a little more cationic character than our secondary carbon. And because this carbon-bromine bond is weaker, it's much easier to attack at the tertiary position to open up this bromonium intermediate. Does that idea make sense to everyone? Does this process, does this underpinning for the mechanism makes sense to everyone? Okay, so let's keep going now. And you can just as easily intercept a polonium intermediate with alcohols or other internal nucleophiles. So again, in this case, if we treat with chlorine, we're going through a chloronium ion. So just to showcase that. So we're working through a chloronium ion. And if we think about our regioselectivity, why do we observe attack at this position? Why do we observe our alcohol attacking only at this position? Would anyone like to offer a reason? Why do we observe this pattern of regioselectivity? Why does our alcohol end up on that carbon? It's tertiary, and to expand on that, in turn the more substitute position that can more readily stabilize a positive charge. And note, our attack occurs from the opposite face of our polonium intermediate, and in turn we generate the following product. The reason why I explicitly chose this particular stereochemical outcome is I'd like you to note that the two possible products are enantiomers. These are non-superimposable mirror images. And if you wanted to finish off this mechanism, you can have water or your alcohol solvent just pull off the last proton to generate your desired final product. Okay, so I just want you to note you do get a mixture of enantiomers and you observe a defined regioselectivity. Okay. Any questions on this so far? Okay, so let's talk a little bit about something that's pretty interesting. So remember how I said that you typically get a mixture of enantiomers? That is true in most cases. However, if you have stereochemical bias as part of your starting molecule, you can observe stereospecificity. And if you start with a single enantiomer, you will get out a single enantiomer. So for example, if an internal nucleophile, so this will be our internal nucleophile, reacts with a polonium intermediate, the stereochemistry of the nucleophile can influence the stereochemistry of the products. Okay, so once we generate our polonium intermediate, let's think a little bit about some non-productive pathways here. So there are two possible polonium intermediates that we can make upon treatment with iodine. So we can either generate the species with the polonium intermediate pointing down, or the polonium intermediate pointing up. Okay, so we have two choices at play. Now, my question to all of you is, looking at our nucleophile, what face is our nucleophile present on? What face is our nucleophile present? Is it on the top or bottom face of our molecule? Where is this nucleophile? Looking at its stereochemistry, it's on the top face. So the internal nucleophile now, because it's on the top face, in order for us to get an attack of our nucleophile on the opposite face to our halonium intermediate, which of these two halonium intermediates is more reactive? The top or bottom intermediate? Which of these two intermediates is more reactive? Which of these two intermediates has the relative arrangement of our nucleophile and halonium intermediate? So let's just label these 1 and 2. Which of these halonium intermediates has the correct relative arrangement of our nucleophile and halonium intermediate for a productive reaction? Number 1 or number 2? Which of these intermediates is set up with the correct relative arrangement of our nucleophile and halonium intermediate for a productive reaction? If our nucleophile attacks from the opposite face, only number 1 can engage in productive, efficient reaction. Number 2, the nucleophile and halonium intermediate are on the same face, which leads to a negligible rate of reaction. They're just not set up with the right orientation for a productive reaction. So as a result, even though our halonium intermediate can be generated on both faces of our alkene, only one halonium intermediate can actually engage in productive and efficient reaction. And as a result, because our nucleophile is so close by, this is a very fast reaction where we end up with attack of our nucleophile to open up our halonium intermediate. And as a result, we observe a single enantiomer if you start with a single enantiomer. We call these kinds of reactions stereospecific, in that the stereoselectivity depends on your starting material. So this is how you can sidestep this issue where the halonium intermediate can form on either face. Of course, there are more sophisticated methods that are developed, but this is a pretty classical method of stereo control in halohydrin formation. And as you notice, there's a wide range of nucleophiles that we can employ, and this really opens up a diverse range of possibilities. Does this idea make sense to everyone? Does this idea make sense? How your starting material stereochemistry can influence the stereochemistry of your product? Perfect. This is super common also in like sugar chemistry, for example. Okay, so we're going to deal with a list of examples. Does anyone notice a particular trend in the examples I'm presenting? Let's discuss this a little bit because it's important to consider. So my first question to all of you, looking at this first alkene, does that look like an E or Z alkene? Yeah, it looks like an E alkene. Well, this alkene, although it can't formally be defined as Z, let's put a substituent here. Let's put a substituent here, just so that way this is a true Z alkene. Okay, the reason why I'm showing you an example of an E and Z alkene participating in these reactions stems from the fact that if you know how an E and Z alkene behave and the stereochemical outcome for an E and Z alkene respectively, you can in turn understand the stereochemical outcome for the reaction of any alkene that you'll see, because the alkene will either be E or Z. So really pay attention to the stereochemical outcome, because these examples were chosen deliberately to highlight the product stereochemistry for the two different types of alkenes you'll encounter. Okay, so let's make a model. So we have to make a model of this first structure. And again, I recommend when you make your model, you use one of the carbon atoms that has five of those modifiable holes in your model kit, because it makes it easier for you to show the attack on the polonium intermediate. Okay, so let's make a model of this structure. It's important that your model be accurate. Otherwise, you're going to end up with a small amount of trouble later on in this section. Okay. So here is our, whoops, one more carbon than I need. There we go. Okay. Oops, let me set. Okay, we're just getting our model kit set up. Okay, can everyone see the model kit on the camera? Can everyone see that on the camera? Okay, so as we notice, we have our ethyl group and our hydrogen on the same side of the alkene, and we have our two methyls on the bottom. Now, is there any preference for what face our bromonium attacks from, be it the top or the bottom face? Is there any preference? Any preference? Does it matter? Can I attack from either face? Yeah. So there's no preference for what face you attack. You can either attack from the top or the bottom face. We're going to show the attack from the bottom face, and we're just going to draw what we see. So this is what happens after we have the attack on the bottom face. So as our first intermediate, we're going to show our N-bromosaccinamide. So we have our N-bromosaccinamide. Okay. We're going to generate our bromonium intermediate. And now we're just going to draw what we see. Okay, so we have our bromonium intermediate on the bottom face. Now, what groups are pointing towards us? What groups are pointing towards us? What's pointing towards us? So like this ethyl group, is it pointing towards or away from us? Towards. So we're going to draw this ethyl group with a wedge. The methyl group gets a dash. Likewise, is this hydrogen pointing towards or away from us? Towards. Yep. So we're going to draw the hydrogen with a wedge, and the methyl group with a dash. Let me just check that everything's on the right face. Okay, so now we have to consider for a moment, when we have water, which is going to be our nucleophile, what position is water going to attack? What position is water going to attack? So we have water. We have water floating around. Okay. Now, what position is it going to attack? The position on the left or the right? Which position is more substituted? Left or right? Which position can more readily accommodate a positive charge? Which position is more substituted? We see a lot of students typing in the chat, the right position. That's exactly correct. Okay, so as we note, we're going to attack on the most substituted carbon, which is the right carbon. And my question to you is there any specificity in terms of what face we attack? Can I attack from the bottom face? Can I go like this? Can I attack from the bottom face? Is this the right arrangement? Am I attacking the sigma star as I'm supposed to? If I'm attacking from the bottom face? No. So I have to attack from the opposite face. And what face would that be? If I'm attacking from the opposite face, what would that be? The top. Okay, so we attack and we pop open our polonium intermediate. Okay, now let's draw that step. So we attack at the most substituted carbon from the opposite face to our bromonium intermediate. Okay, so now we have our alcohol pointing up. Okay, we have our methyl in the back, our ethyl in the front. Okay, so now that we have this set up, let's just draw a quick deprotonation step. And this works just because we have an absolute boatload of solvent available, so we can readily just disperse that proton. These reactions are also typically run under buffered or mildly basic conditions, just to cut down on the relative amount of acid in solution so you don't get random elimination products. Okay, so here's our product, okay? Now, let's try to draw this product in a little bit more of a common conventional way. So, as we notice, we still have each of our substituents that are on the same side of our alkene end up on the same side on our product. Okay, now let's look at some rotations. And let's try to visualize this molecule from a few different perspectives. So the first perspective that I want to show you, the first perspective that I want us to look at is the perspective where we have our methyl groups set up and they're just directly sitting in the plane of the page. So this is an equivalent structure. So let's draw our first equivalent structure. So if we have our methyl groups and all of our carbons sitting in the plane, we have 1, 2, 3, 4 carbons arranged like so. So we've drawn our skeleton. Now let's look at what species are pointing towards us. So what's pointing towards us? What's pointing out of the page towards us right now? So let's start with the right-hand side. What is pointing out towards us on the right-hand side? Is that a methyl group? Let me show this a little more. Is that a methyl or an ethyl group? This group here. It's an ethyl group, exactly right. Another student correctly chimed in that the bromine is pointing towards us. Okay, now what's in the back? What's in the back? It's hard to see, but what's in the back? The hydrogen, yep. And the hydroxy group. Does that make sense? Okay, here's another equivalent structure. Let's look at the common zigzag bond arrangement. Let me show the other one because that's more common. Okay, so in this case, we have our basic skeleton in the typical zigzag pattern for a typical straight chain alkane. Now let's identify what substituents are pointing towards us. So starting on the left, what's pointing towards us? What's pointing towards us? Bromine, yep. So we'll give the bromine. Okay, what about this alcohol? Is that pointing towards or away from us? Towards, yep. And then the ethyl group is pointing away from us. So these three versions of our structure are all identical. If you don't believe me that they're identical, well, first we showed that via rotation. You can also prove that to yourself via assignment of the stereochemistry. So if you're curious, this center is R. And notice how in this structure, the center is also R. And it's also true in this structure for that matter. So there's always a way of checking your work. So if you're ever unsure if the form that you've drawn is correct, you can always go through and you can assign the stereochemistry. Does this process make sense to everyone? Does this process make sense? Now, there are many perspectives that you can view these molecules from. So you may have to rotate your molecule a little bit to get it in the right position and set up in the right way for you to observe the stereochemical outcome. Okay, now that we've understood and now that we've identified our possible stereochemical outcomes for our E alkene, let's look a little bit at the Z alkene. One thing I do want to note, however, is that we also get the enantiomer. So if we want to look at the enantiomeric product possibility, we'd attack from the top face. And in turn, we get the enantiomeric products. And you can prove that to yourself as well. So always keep in mind you get a mixture of the product and its enantiomer. Okay, so let's look at this next case where we have our alkene. And just as always, we have our first step where we generate our bromonium intermediate. So let's make a model of this structure. Let's make a model of this structure. So let's take a moment to make a model of this structure. And please make sure you're actually following along and making your own model kit. Because if you don't learn how to use the model kit as part of dealing with the content, then it's going to be difficult to just pick up the model kit and use it to make meaningful interpretations. Okay. Okay, so here is our structure. Here is our structure. We have our alkene, and we can attack from either the top or the bottom face, right? There's no preference for what face we attack from. Does that idea make... Oh, sorry, this methyl group's on the wrong side. One moment. There we go. Okay, perfect. So we've directly matched our structure in our drawing. Okay, so now we can either attack from the top or the bottom face. Is there any preference? Is there any preference? Is there any preference for which face we attack from? In this case, there's not a lot of bias in terms of which face is preferred. So we get a mixture of attack from the top and the bottom face. In most cases, you always observe a mixture unless there's a strong biasing factor in your molecule. So we're going to generate our bromonium intermediate. Okay, so we've made our bromonium intermediate. And now what we're going to do is we're just going to draw what we see. We're just going to draw what we see after generation of this bromonium intermediate. Okay, so for this bromonium intermediate that we have, let's take a look and let's try to identify what things are in front, what things are pointing towards us, what two things are pointing towards us. So what's pointing out towards us on the right? What is pointing towards us on the right? What's pointing towards us? What is pointing towards us on the right-hand side of our molecule? The methyl group, exactly. So then, in drawing this out, so we have our bromonium intermediate on the bottom, we have our methyl group pointing out towards us, and what is pointing away from us? What is pointing away from us? Hydrogen, exactly right. Okay, now my question is, for the ring system, what is pointing, so for the ring system, the side with the methyl group is pointing towards us. Right? Can everyone see that? How the side with the methyl group is pointing towards us? Okay. So now once we have this halonium intermediate, what face is water going to attack from? What face is water going to attack from? If the bromine is on the bottom face, where is water going to attack from? Is it going to attack from the bottom face too, or the top? So we see in the chat, it's going to attack on the top. Now, which site will it choose? Which site will it choose? Will it attack on the left or right-hand side of our bromonium intermediate? Which side is more substituted? Which side is more substituted? The left-hand side, exactly right. So we open up our halonium intermediate via attack from the top face on the left-hand side. So we pop open our halonium intermediate, and that in turn gives us the following product. Now all we have to do is draw what we see. Now all we have to do is draw what we see. Okay, so just to check that my drawing is correct. So we have our ring, and we have the side with our methyl group in front. We have our alcohol on top. We have our bromine on bottom, and we have the methyl group in front. So everything checks out so far. So now what we're going to do is we're going to look at this molecule as if it were completely flat. So we're just going to put the ring into the plane of the page, and we're just going to draw what we see. So we're going to just put the ring into the plane of the page, and then we're going to draw what we see. So our goal is just to be as detailed as possible when it comes to our depiction of the stereochemistry, and to be able to correctly indicate all of the major stereochemical outcomes that we will encounter as part of this halohydrin formation reaction. Okay, so let's draw out some equivalent structures. So I placed my entire ring in the plane of the page, and now we're just going to draw what we see. So we have our ring completely flat in the plane of the page. Okay, drawing out what we see. Continuing on with that, we have our methyl group right here. Okay, and now, which groups are pointing out towards us? Which groups are pointing towards us? So which groups are pointing towards us? The alcohol, yep. Let me angle this a little bit differently so it exactly matches the drawing. So the alcohol is pointing towards us. Okay, what else? What else is pointing towards us? What else is pointing towards us? The hydrogen, yep. Okay, and let's be really particular here. So if our hydrogen is pointing towards us, what group is pointing away from us? What group is pointing away from us? What's this group in the back? The bromine. Yep, exactly right. So let's just showcase that one more time for us to see. So we have our alcohol pointing towards us, we have our hydrogen pointing towards us, and our bromine pointing away from us. Now, if we wanted to, we can just as easily rotate this bond so that our bromine's pointing towards us. So this structure is also equivalent. Now, one thing we have to pay attention to is that our skeleton has changed in terms of how we've drawn and oriented the skeleton of our chain and of our molecule in 3D space. So keep in mind, all of these structures are equivalent. All we're doing is just rotating our bonds. Does everyone see how in this first orientation, the bromine is away from us, while in this orientation, the bromine is pointing towards us? Does that make sense? Okay. So again, we've covered all the different ways of drawing out your molecule to correctly and fully show the stereochemical outcome. This is a skill that you'll have to employ, and you'll have to pay special attention to what alkenes you're given, because the stereochemistry of your alkene directly impacts the stereochemistry of your halohydrin. Any questions on this? And of course, we also get the enantiomer. Which, just shown for a complete depiction, would have the bromine on the top face. Okay, so now that we've seen some examples, let's take a look. Let's take a look at the following problem. And let's try to draw a mechanism for this reaction and predict the stereochemistry of the products from this reaction. So the first thing that you're going to have to do is identify this alkene. So is this alkene going to be E or Z? So this alkene is E. Yep. Okay. So from that, I'd want you to tell me exactly the stereochemistry of these two centers. That's what we're interested in. We have an E alkene. What would the stereochemistry be? And to answer this question fully, you will have to make a model. You will have to make a model of your structure. That's my hint for this problem. So I'd like to see some students sharing their proposed structures and mechanisms using the annotate tool. And then from there, let's try to build on, draw the complete mechanism, and really showcase the stereochemical outcome of this reaction. So you can either draw this final product and indicate the stereochemistry, or you can show the step-by-step processes, which you'll need to as part of this problem. So that way I can comment and provide feedback. Make sure you draw the intermediates for each step with the right stereochemistry, as that'll help guide you towards the correct answer. So let's take about 4 to 5 minutes to work through this example. You will need a model kit for this, or you're going to need to be very careful and detailed with your drawings, but I recommend you use your model kit as it's far easier, especially for these types of structures. This is an example of an attack by an internal nucleophile. In this case, in case you're wondering, the regioselectivity is dictated by ring size. So it's a pretty funny quirk of this reaction. So don't be shy to share your responses using the annotate tool, and I'd be happy to provide feedback. Really want you to work through this problem and give your best attempt at it, because that's where a lot of the development happens, when you're working through a problem, trying to figure it out, and drawing or trying to draw reasonable conclusions based on what you see with your model kit and how you've drawn out the mechanism for this reaction. And don't be shy to share your responses using the annotate tool or in the chat as a picture. And don't be shy to ask a question in the chat or verbally. So does anyone have a proposal that they'd like to share for this mechanism using the annotate tool? Does anyone have a proposal for this mechanism that they'd like to share? Would you be able to draw out the stereochemistry in the structure just so that way the class can visualize it? So you have an assignment where both these stereocenters are R. Would you be able to share your annotated structure? Okay, perfect. So we have the proposed stereochemical assignment. Does anyone else have a proposal for the product stereochemistry? Would anyone else like to share their proposed stereochemical assignments for the product? Let's give everyone about another minute, and then we'll talk through this question using our model kits. Okay, so let's take a look at how this is going to pan out. Let's take a look, and let's first just make sure that we put together our model kit appropriately and that everything has all the stereochemical assignments look good. Okay, so let's get that set up. Okay, so let's just check to make sure that everything is in the right spot for our reactant. Okay, so we have our straight chain. We have both of our hydrogens on our alkene trans, and we have this long chain containing our alcohol. That's our nucleophile in this process. Okay, so now what we're going to do is we're going to attack with our halonium. We can either attack from the top or the bottom face. Is there any preference? Again, is there anything biasing in this molecule? Any stereochemical bias? What do we think? Is there any preference for the top or the bottom face? No preference, so let's just arbitrarily choose the attack from the bottom face. Of course, we'll get a mixture of enantiomers. Okay, so now that we have that set up, now that we have our first step set up, we are just going to draw what we see. We're just going to draw what we see. Always want to make sure that we're able to see the mechanistic steps for this reaction. Okay, so we have our bromine, and it's on the bottom face, okay? Okay, now, what species are in front? What atoms are in front? What's the first atom that's in front on the left? What's in front on the left? Hydrogen, okay? And in turn, by deduction, the methyl's in the back. Okay. What else is in front on the right-hand side? What's in front? What's in front? Is this chain right here in front or in back? It's in front. Now, I'd like to draw your attention to a very important detail. Do you notice how the hydrogens are trans? Do you notice how these hydrogens are trans to each other? And do you notice how in our halonium intermediate, the hydrogens are also trans? Does that make sense? So make sure to check that your halonium matches your alkene. Okay, now here's the pretty cool part. We know that we're getting a 6-membered ring, right? We know that we're getting a 6-membered ring. So in turn, all we have to do is count our carbons. 1, 2, 3, 4, 5, 6. And we have a tack to yield our 6-membered ring product. For these kinds of intramolecular processes, you have competition between 5 and 6-membered ring formation. Favorability for ring formation is a topic that will be covered in more detail in the next organic class, because we'd have to talk a little bit about the cyclization rules. In general, 6-membered rings are more stable, while 5-membered rings are often the kinetic product. We're going to just presuppose that we have a tack to generate a 6-membered ring. Okay. Okay, now it's really important to note when our alcohol attacks, is it going to attack from the bottom face or the top face? It's going to attack from the bottom face or the top face. How will it attack? Will it attack on the same side as this bromonium or the opposite side? What does everyone think? Same or opposite side? What's our rule for halohydrin formation? Does the attack occur on the same side of the bromonium intermediate or the opposite side? Do we get cis or anti products? Attacks on the opposite side. So we end up with an anti product distribution. Okay. Okay, so now that we have shown our attack, now what we're going to do is we're just going to draw what we see. We're just going to draw what we see now. Okay, so we've attacked, we've opened up our ring. We have this 6-membered ring. Okay, so now, as always, we still have our hydrogen in front and our methyl in the back. Does everyone see that on this leftmost carbon? We have our hydrogen in front, our methyl in the back. Now, looking at the carbon containing our bromine, we have what group in front? What is in front and what's in back? What's in front and what's in the back? What do we have stuck in the back? Front is carbon, back is hydrogen. Good, good. That's great to see. Okay, now this is a bit of a wonky perspective to look at your molecule from, so we're going to rotate it to make it a little bit easier for us to view. So this isn't exactly the perspective that we want to be viewing our molecules from. We typically like to have our rings sort of drawn into the plane of the page rather than pointing out or into the page. Okay, so to accomplish that, we're just going to rotate our view. So we're going to rotate our view of this molecule, and we're going to draw the ring just sort of flat in the plane of the page. And we're just going to rotate our perspective so our perspective matches the template. So now that we've rotated our molecule to match our desired perspective, we're then just going to draw what we see. So starting off with the first species, starting off with the first carbon closest to the oxygen, is this hydrogen pointing towards or away from us? Is this hydrogen pointing towards or away from us? Where's this hydrogen pointing? What do we think? Towards or away after rotation? Towards, right? So we have the hydrogen pointing towards us. And what about this methyl group? Is it pointing towards or away from us? How's this methyl group? It's pointing away from us. Yep. Okay. What about the bromine? Is it pointing towards or away from us? Towards, yep. And what about the hydrogen? It's pointing away from us. Okay, so there we go. So as we notice, let's just look at our stereochemistry for a moment. Let's just look at our stereochemistry for a moment. So this center is S. This center is R. We can check our work because this center is still assigned as R. And this center is still assigned as S. Of course, you also get the enantiomer. So if you ended up with a structure with the exact opposite configuration at both of the centers, you were essentially drawing the enantiomer, likely because you had a different attack from your bromonium intermediate. Does this example make sense to everyone now? This is something that you're going to have to do, and it's one of the skills that I view as very important in this class. Not just to draw mechanisms without stereochemistry, but being explicit into what stereochemistry you're generating for your products. Because the whole point of these reactions, many of these reactions, are not the fact that they make a racemate, is that they generate a defined set of stereochemical outcomes depending on your starting material. We spend all this effort making this alkene with the specific stereochemistry. The reason why we start with an E-alkene is to generate these two stereocenters that are fixed based on the stereochemistry of our alkene. Stereospecificity is a very powerful tool, and understanding the stereochemical outcome of reactions can help you understand and explain and logically piece together a path to go from a starting material to a product in a defined manner. So that's the broader goal. So make sure you understand the stereochemical outcomes. That's why I do the walkthroughs with the model kit. And this particular reaction is important to know because it's a super class of mechanism that many of these other reactions are going to follow. With that in mind, let's look at this next class of reaction known as oxymercuration. And I have to say, mercury is pretty interesting in terms of the reactions it facilitates. If it weren't for the fact it was pretty toxic and not entirely pleasant to handle, it's quite a useful reagent in terms of the unique things that it can do. It's been supplanted by some other reagents recently, but it still has its place. So you can hydrate an alkene via oxymercuration through a two-step process of oxymercuration followed by reduction of the alkyl mercury species with sodium borohydride. Now, what's really cool about mercury, and the one thing I always like to remember is mercury is huge and it hates steric strain. So the unique thing about oxymercuration is that addition of water occurs from the most hindered face anti to the mercurinium ion. Okay, so again, we have this anti-stereochemical preference, but this time water is going to add on the most hindered face. Addition of water follows Markovnikov selectivity, with water adding to the most substituted carbon. Okay. The way that I like to think about it is mercury ends up on the least hindered carbon. And face. Okay, so in oxymercuration, so we have our alkene. Let me draw out. Mercury acetate's the most common reagent. You end up with coordination of the mercury to our alkene. We end up with our mercurinium intermediate. What does this remind everyone of? What does this remind everyone of? Does this intermediate look very familiar to us? Does this cyclic three-membered ring intermediate with a positive charge, what does that remind everyone of? Does this look familiar to anyone? Going all the way back up here. The halonium intermediate, exactly right. Mechanistically, these two reactions can be thought of as a pair of complementary reactions. This mercurinium ion is very similar to our halonium intermediate. And our regiochemical outcome is also similar. We end up with the attack on the most substituted carbon with anti-stereochemical selectivity and Markovnikov regioselectivity. So first we end up with generation of our mercurinium ion by coordination onto our alkene. Then water attacks, and water is going to attack at the most hindered carbon anti to our mercurinium ion to yield Markovnikov regioselectivity and anti-stereoselectivity. The one unfortunate thing to note is that the mercury stereocenter is often racemized during reduction. So this hydrogen that is derived after reduction of the mercury, you don't often get a lot of stereo control for that hydrogen. Okay. One thing to note and one benefit of oxymercuration compared to acid catalyzed processes is that oxymercuration avoids rearrangements observed under strongly acidic conditions. Just as a reminder, if we took this alkene and I tried to hydrate it using H3O+, remember, what we saw was not our desired hydration product. Instead, we got a bit of a mess. So oxymercuration serves as a somewhat more selective method of alkene or olefin hydration, because it sidesteps a lot of the inherent issues going through a carbocation intermediate. So if we tried to treat this alkene with acid, we would get out this alcohol, and we wouldn't exactly be very happy about that. So the main benefit of oxymercuration is that it avoids rearrangements. We only observe a single product. And another benefit of oxymercuration is it generates our product with a defined stereochemistry. Does everyone see the contrast between oxymercuration and olefin hydration under acidic conditions? Does everyone see how in oxymercuration, because we are not going through a carbocation, we have sidestepped the issue of rearrangements? Does that make sense to everyone? Any questions so far? Okay. So unfortunately, as we've talked about earlier, reduction occurs with loss of stereochemistry at the carbon containing the mercury atom in most cases. So this has been shown experimentally. If you reduce with the deuterium analog of sodium borohydride, you see a mixture of enantiomers. You see a mixture of incorporation of deuterium and a mixture of stereochemical outcomes for the reduction at that stereocenter. You do set the alcohol stereocenter with stereo control. Okay. So oxymercuration overwhelmingly occurs via anti-addition following Markovnikov stereochemistry. So just to highlight the steps once again, first we coordinate mercury and we generate our mercurinium ion. This can occur at either the top or the bottom face. It doesn't matter. Both the faces are equivalent. What does matter, however, is for our subsequent attack. So just to make sure we're clear, does the attack of our alcohol occur at the same or opposite face? Does the attack of our alcohol occur at the same or opposite face to our mercurinium ion? If it's occurring via anti-addition, will the attack occur at the same or opposite face? What does everyone think? So because it occurs via anti-addition, our alcohol is going to attack and add from the opposite face to our mercurinium intermediate. In turn, giving us the anti-addition product. Now, of course, this stereocenter with our mercury atom gets racemized during reduction. But it's important to note because, as you'll learn in later classes, there are means to intercept this alkyl mercury species and use it for further reaction. Okay, so this is a good stopping point for today. What we'll do is we'll pause the recording